Okay, I think we'll get started. So this is Machine Learning for General Chemistry 2, lab number 2. And we're going to be focusing on this idea of chemoinformatics, or chemoinformatics as they're sometimes called. And we're going to be modeling in a very simplistic way a drug-protein match. So the drug-protein interaction, you might imagine that we want to get a drug to bind to a protein, an important protein in the body, that will elicit some sort of physiological response. And the idea behind chemoinformatics is that you have a molecule that, say, binds to this site, and then what you do is you take an expansive library of molecules that are very similar to this one, and then you test it against that protein. And you would anticipate that some will do well for eliciting the right response from that protein, and some won't do well. And so it's kind of a probabilistic approach. You shoot out all these different possible structures that are similar to one that you know kind of works, and then you hope you get one that does work. Well, you can combine this in what's called an evolutionary algorithm, where you then take the best, or best, say, 5 of those molecules and do the whole thing again. So blow out another 100 or so molecules and then take the best 5 of those and the best 5 of those. And as you have go through several generations, as they're called, then you get better and better binding of a particular molecule to this site on the protein. And presumably a better binding means a better physiological response, or a more responsive drug, or a more selective drug, something that you're selecting for. So it really combines, well, it really sort of uses the idea of evolution. That's why these are called evolutionary algorithms. So in our particular case, what we're going to do is we're going to imagine a one-dimensional protein and a ligand, and that ligand will interact with that protein at 100 sites or places, and the interaction will be just some generic type of how that ligand wants to sit next to that protein, and it could be related to hydrophobicity or electrostatics or whatever in terms of what's going to snuggle that protein in with a good binding energy. And we're going to take an approach where we have control over all 100 points along here, and we're going to just throw out a random molecule, see how good it does, then throw out another random molecule, see how good it does, rank them according to which interacts most strongly or has the lowest binding energy, so the most stable binding energy. We were going to rank those, and then we'll take the best one and then perturb that in a bit. So not just start completely over with a random set of 100, but take the one we have and then perturb each of the sites randomly, but under a certain constraint. So we won't do a dramatic change to each site, but a small change to each site. Then rank those, and so on and so on and so on. And what we'll see is that with a remarkably small number of generations, you get a protein that matches very, very well, or you get a ligand that matches the protein very, very well. So let's go to the computer and run through this. Okay, so we should be in this lab, and you should have the ChemAI launcher up and going here. If you are just coming to this lab without previous work on this, the first video in this playlist goes through how to get this onto installed on your computer. Okay, so we'll just kind of, so this is the lab manual. Sort of very quickly go through this. So we're of course talking about chemoinformatics, or sometimes called chemoinformatics, and talking particularly about these evolutionary algorithms. So it's not just blindly making random chemicals, but making a set of random chemicals and then choosing the best ones and then perturbing each of those individually. Okay. Then we're modeling drug discovery here, so we're looking for a ligand or a drug that will bind with a strong binding affinity, so a lower energy value. So we want a good, strong negative value for our binding energy. What we're shooting for here is we've got this protein site, and it just has a particular arrangement of values. This is just something that I chose. It could have really been anything, and so they're just color coded. And a match, visually, we'll see a match as a red match with the red and blue matches with the blue. That means a good fit. If it's a red with a blue, then that's a bad fit. It's higher in energy or unstable. Red with red or blue with blue is more stable. And so we'll get favorable energy values for that. And so we'll just see how good we can get this to look like this, basically, is what we're doing. And so I won't say too much. I guess I don't say much more about that. Let's jump right into the experiment. So chemoinformatics, and we'll open that up. And what we're looking at here now is, let's go ahead and just present some ligands. So we're not going to jump into the process quite yet. We're just going to see what happens. So this is going to be a random ligand. And we see very poor match. Energy value here, it will be in red when it's positive, green when it's negative. But it's the only one we presented, so it's our best ligand so far. So let's present another one, so completely random again. And I think this is worse. Yeah, this is worse. So the one we had before was a better fit, even though it doesn't look that good. And then again, and again, and again, and again, and again. And finally, we can find some that are better. This one is terrible. So we're getting this ranking here. So what we're going to do now is we're going to run a seed generation, or generation 0, where everything is just random, completely random, 100 random ligands. And the top 3 are going to be ranked up here. So let's run the seed generation. And we see the top 3 coming in. Okay. Now, not very good, because these were all random. There's only 100 of them. The chance that we get one that's going to look like the protein site is essentially 0. Now, we're gonna have a perturbation level 0.5. So this is a little bit scaled, so it's hard to know exactly what this means. But what we're going to do is we're going to take this. When we run the next generation, it's going to take this one alone, and then at each one of these, it's going to adjust it a little bit. Basically, it's going to adjust it by no more than 5% of what it was before. So that's a way you can read that. Okay, so let's run the next generation. So this will be generation 1. And we'll see here on this graph, the values come in, and better and better ones will start coming up. We can already see kind of a more preponderance of blue here and a more preponderance of red here, although still an unfavorable interaction. But it's come down considerably here to 0.2. So it was, I think it started up here, so it came down here. Okay, let's run generation 2. Let's run this next generation. And we see that we keep making progress. We've actually gone, I think I said green, but blue here. We've gone negative in energy, so starting to get a favorable binding. And we're definitely seeing this start to look a bit more like what the protein looks like. But still lots of places where it misses. So we'll run the next generation, this generation 3. Again, we keep making slow progress, less progress than we did before, because we're starting to get closer to what this should look like, or have the best match. And now we're very much starting to see a decent match here. Well, let's keep running a few. I will just keep running until we don't see very good progress. And then we will adjust the perturbation level. And what we want to do is bring it down. So you can make good progress early on if your perturbation level is high, but then you come to some kind of plateau. So then if you drop your perturbation level, you can make some additional progress. So we are still making progress. So let's keep running this. I'll run it out to 10 generations, let's say, and then we'll change the perturbation level. Oh, we're still getting good progress here. So. Okay, so not much progress there. I'll do one more generation here. And we really have stagnated now. Might get a lucky shot that comes in. Looks like we did get a little bit lucky here compared to the 9th generation. But now let's go ahead and lower this. And we should see improvement here now. And yeah, we see, some fairly decent improvement on where that was starting to stagnate. Very much getting to look pretty close to the protein. But we'll run this, let's run this out a few generations, and then we will set the perturbation level even lower, and then I think you'll probably have a good idea of what's going on here if you haven't already. Okay, we're making good progress, starting to look very similar. I'm going to pause this, go a little bit further, and we'll see just how good we can get here. Okay, so gone 30 generations, and you can kind of see this curve go. Here's where we switched a different perturbation. I switched a different perturbation here, and then here again. So I think this was 0.05, 5%, 1%, 0.5%, there's a 5%, 1%, 0.5% to here, and then I did 0.1%. And you can see here now the match is pretty extraordinary. Not exactly perfect, but very difficult by eye to tell. And so even after 30 generations, this 100 random sites, starting off completely randomly, falls into place pretty well. All right, so what you will do is play around with this a little bit, and then you'll have a little contest with the class or just with yourself. See how low of an energy you can get in, let's say, 5 minutes, or let's say after 50 generations, or even 30. See if you can beat. I got minus 25, and so actually it should be minus 25.16. So you can see if you did any better than that, and you can get a little feel for what role the importance of the perturbation level is. I think by playing with that yourself, you get a better sense of that than just watching me do it. All right, so that's it for this lab. See you in the next one.